In this video, we're going to look at pairs of molecules and see if they relate to each other in any obvious way, or maybe less than obvious way. So these first two right here, they actually look like completely different molecules. So your gut impulse might be, see, these are completely different molecules, and it wouldn't be completely off. But if we look a little bit closer, you see that this guy on the left has 1, 2, 3, 4 carbons, and so does this guy on the right. He has 1, 2, 3, 4 carbons. This guy on the left has 2, 4, 6, 7, 8 hydrogens. This guy on the right has 2, 4, 6, 8 hydrogens. And they both have 1 oxygen. So both of the molecular formulas for both of these things are 4 carbons, 8 hydrogens, and 1 oxygen. They're both C4H8O. So they have the same molecular formula. They're made up of the same thing. So these are going to be isomers. They're going to be isomers, and they're a special type of isomers. In this situation, we don't have the same bonds. We're made up of the same things, but the bonds, what is connected to what, is different. So we call this a constitutional isomer. Constitutional isomer. So we are essentially made up of the same things, but we are actually two different molecules, actually two very different molecules here. Now let's look at this this next guy over here. So if we look at this molecule, let's see, it does look like this carbon is chiral. It is an asymmetric carbon. It is bonded to 4 different groups: fluorine, bromine, hydrogen, and then a methyl group. And so is this one. And they're both made up of the same things. You have the carbon, and not only are they made up of the same things, but the bonding is the same. So carbon to a fluorine, carbon to a fluorine, carbon to a bromine, carbon to bromine, carbon to hydrogen in both, and then carbon to the methyl group in both. But they don't look quite the same. Are they mirror images? Well, no. This guy's mirror image would have the fluorine popping out here, the hydrogen going back here, and then would have the bromine pointing out here. Let's see if I can somehow get from this guy to that guy. Let me flip this guy first. So a good thing to do would be to just flip. Let me see the fastest way I could potentially get there. Well, let me just flip it like this. So I'm going to flip out of the page, you can imagine. I'm going to flip it like this. So I'm going to take this methyl group and then put it on the right-hand side. And you can imagine I'm going to turn it so it would come out of the page and then go back down. So if I did that, what would it look like? I would have the carbon, this carbon here. I would have the methyl group on that side now. And then since I flipped it over, the bromine was in the plane of the page. It'll still be in the plane of the page. But since I flipped it over, the hydrogen, which was in the back, will now be in the front. The hydrogen will now be in the front, and the fluorine will now be in the back because I flipped it over. So the fluorine is now in the back. Now, how does this compare to that? Let's see if I can somehow get there. Well, if I take this fluorine and I rotate it to where the hydrogen is, and I take the hydrogen and rotate it to where, well, it's all going to happen at once, to where the bromine is, and I take the bromine and rotate it to where the fluorine is, I get that. So I can flip it, and then I can rotate it around this, I guess, this bond axis right there, and I would get to that molecule there. So even though they look pretty different, with a flip and a rotation, you actually see that these are the same molecule. Same molecule. Next one. So let's see, what do we have here? Let me switch colors. So over here, this part of both of these molecules look the same. You have the carbons on both of them. This carbon looks like a chiral center. It's bonded to 1, 2, 3 different groups. These are, you might say, oh, it's 2 carbons, but this is a methyl group, and then this side has all this business over it. So this is definitely a chiral carbon. And over here, same thing. It's a chiral carbon. And this has the same thing. It's bonded to 4 different things. So each of these molecules have 2 chiral carbons. And it looks like they're made up of the same things. And not only are they made up of the same things, but the bonds are made in the same way. So this carbon is bonded to a hydrogen and a fluorine, and then 2 other carbons, same thing, a hydrogen and a fluorine, carbon. It looks like it's a hydrogen. It's bonded to a hydrogen and a chlorine. So it's made up of the same constituents, and they're bonded in the same way. So these look like but the bonding is a little bit different. Over here on this one on the left, the hydrogen goes in the back, and over here the hydrogen's in the front. And over here the chlorine's in back, and over here the chlorine's in front. So these look like stereoisomers. Stereoisomers. You saw earlier in this video, you saw structural isomers, made up of the same things, but the connections are all different. Stereoisomers, they're made up of the same thing. The connections are the same, but their three-dimensional configuration is a little bit different. For example, here on this carbon, it's connected to the same things as this carbon, but over here the fluorine's out front, and over here, out here the fluorine's out front, over here the fluorine's backwards. And the same thing for the chlorine here. It's back here and it's front here. Now, let's see if they're related, I guess, in a more nuanced way. Well, if you put you can imagine putting a mirror behind. If you put I guess the best way to visualize, imagine putting a mirror behind this molecule. If you put a mirror behind this molecule, what would its reflection look like? So if you put a mirror behind it, in the image of the mirror, this hydrogen would now, since the mirror is behind this whole molecule, this hydrogen is actually closer to the mirror. So then the mirror image, you would have a hydrogen that's pointed out, and then you would have the carbon, and then you would have the fluorine being further away. And same thing in the mirror image here, you would have the chlorine coming closer, since this chlorine is further back, closer to the mirror. And then you would have the hydrogen pointing outwards like that. And then obviously the rest of the molecule would look exactly the same. And so this mirror image that I just thought about in white is exactly what this molecule is. Hydrogen pointing out in front, hydrogen pointing out in front. You might say, wait, this hydrogen is on the right, this one's on the left. It doesn't matter. This is actually saying that the hydrogen's pointing out front, fluorine's pointing out back, hydrogen out front, fluorine back, chlorine out front, hydrogen back, chlorine out front, hydrogen back. So these are actually mirror images, but they're not the easy mirror images that we've done in the past where the mirror was just like that in between the two. This one is a mirror image where you'd place the mirror either on top of or behind one of the molecules. So this is a class of stereoisomers, and we've brought up this word before. We call this enantiomers. Enantiomer. So each of these are an enantiomer. I'll say they are enantiomers of each other. They're stereoisomers. They're made up of the same molecules, so they have the same constituents. They also have the same connections. And not only do they have the same connections, that so far gets us a stereoisomer, but they're a special kind of stereoisomer called an enantiomer, where they are actual mirror images of each other. Now, what is this one over here in blue? Just like the last one, looks like it's made up of the same things. You have these carbons, these carbons, these carbons, and hydrogens up there. Same thing over there. You have a hydrogen, bromine, hydrogen and a bromine, hydrogen and chlorine, hydrogen, chlorine, hydrogen, chlorine, hydrogen, chlorine. So it's made up of the same things. They're connected in the same way. So they're definitely stereoisomers. Well, we have to make sure they're not let's make sure they're not the same molecule first. Here, hydrogen's in the front. There, hydrogen's in the back. Here, hydrogen is in the back. Here, hydrogen is in the front. So they're not the same molecule. They have a different three-dimensional configuration, although their the bond connections are the same. So these are stereoisomers. These are stereoisomers. But let's see if they're enantiomers. So if we look at it like this, you put a mirror here, you wouldn't get this guy over here. Then you would have a chlorine out front and a hydrogen. So you won't get it if you get a mirror over there. But if we do the same exercise that we did in the last pair, if you put a mirror behind this guy, and I'm just going to focus the stuff that's just forward and back, because that's what's relevant if the mirror is sitting behind the molecule. So if the mirror is sitting behind the molecule, this hydrogen, or this bromine, is actually closer to the mirror than that hydrogen. So the bromine will now be out front, and then the hydrogen will be in back. This hydrogen will be in the back. If you're trying to do kind of a mirror image, if it's hard to conceptualize, and then that would all look the same. And then this chlorine will now be out front, and this hydrogen will now be in the back in our mirror image, if we can visualize it. And then we have another one, and then this chlorine is closer to the mirror that's kind of sitting on top of. So in the mirror image, it would be pointing out, and then this hydrogen would be pointing back. Now let's see, is our mirror image the same as this? So in the mirror image, our bromine is pointing in the front, hydrogen in the back there. Then we have hydrogen in Then in our mirror image, we have the hydrogen back, chlorine in front, same there. So far it's looking like a mirror image. And then in this last carbon over here, chlorine in front, hydrogen in back. But here we have chlorine in the back, hydrogen in front. So this part, you could think of it this way. This is the mirror image of this. This is the mirror image of this part. But this is not the mirror image of that part. So when you have a stereoisomer that is not a mirror, when you have two stereoisomers that aren't mirror images of each other, we call them diastereomer. I always have trouble saying that. Let me write it. These are diastereomer. Diastereomers, which is essentially saying it's a stereoisomer that is not an enantiomer. That's all it means. Stereoisomer, not an enantiomer. A stereoisomer is either going to be an enantiomer or a diastereomer. Now let's do this last one. Let's see. We have this kind of cyclohexane ring, and you have a bromo on I guess the number 1 and the number 2 group, depending how you think about it. It looks like they are mirror images of each other. We could put a mirror right there, and they look like mirror images. And this is a chiral carbon here. It's bonded to one carbon group that is different than this carbon group. This carbon group has a bromine. This carbon group just has a bunch of hydrogens on it if you kind of go in that direction. So, and it is hydrogen and then a bromine. So that is chiral. And then same argument, that is also chiral. And obviously this one is chiral and that is chiral. But if you think about it, they are mirror images of each other, and they each have two chiral centers, or two chiral carbons. But if you think about it, all you have to do is flip this guy over, and you will get this molecule. These are the same molecules. So it is the same molecule. So this is interesting. And we saw this when we first learned about chirality. Even though we have two chiral centers, this is not a chiral molecule. It is the same thing as its mirror image. It is superimposable on its mirror image. It is superimposable on its mirror image. So even though it has chiral carbons in it, it is not a chiral molecule. And we call these meso compounds. Meso compound. This is and we can point to one of them because they really are the same compound. This is a meso compound. It has chiral centers. It has chiral carbons, I guess you could say it, but it is not a chiral compound. And the way to spot these, fairly straightforward, is that you have chiral centers, but there is a line of symmetry here. There is a line of symmetry right here. These two sides of the compound are mirror images of each other. Now, these would not be the same molecule if I changed that to a fluorine and I changed that to a fluorine. Then all of a sudden you do not have this symmetry. These are mirror images, but they would not be superimposable. So if that was a fluorine, these would actually be enantiomers. And this would not be only one meso compound. It would be two different enantiomers, and one of them would have a R direction, and one of them would have an S direction if we go with the naming conventions that we learned in the